Thank you. So I would like to thank the organizers for inviting me here. It's lots of fun, and also it's great to celebrate your combined birthdays. So I'm going to be talking about HSL numbers, and these are going to be invariants that are defined in characteristic P. So let's agree that from now on, whenever you see a ring, it's going to be commutative, Noetherian, and prime characteristic P. So why do people like looking at rings of prime characteristic P? They come automatically equipped with extra structure. So we have Frobenius maps, which I'm going to call FE, that go from R to R, and they raise things to the P to the E powers. And this is a ring homomorphism. And what can you do with these ring homomorphisms? Well, you can do lots of interesting things, but one of them is you can expand ideals using this ring homomorphism. So let I be an ideal. Let's define Fe of I to be the expansion. The expansion of I under this homomorphism Fe, and this is the ideal generated by all P to the eth powers and elements in I. And I'm going to have another notation for this expansion. I'm going to call this I to the square bracket P to the E, the P to the eth Frobenius power of this ideal. And I can also contract things under this map. So let's start with this ideal I. Here it is. And let's expand this. And let's contract this. And let's do this for all e's greater or equal to 0. And what you're going to get here is an ascending sequence of ideals. And I can take the union of that over all the e's greater or equal to 0. This is going to stabilize at some point, and I'm going to give a name to this stable value of this ascending chain. This is going to be the Frobenius closure. Frobenius closure of this ideal I. And since we're working in the Noetherian ring, this is going to be some eta, the value of this for some e is equal to some value, which I'm going to call eta. So I'm going to write this as f eta contract, f eta expand for some eta. Okay, so here's the first application we're going to have to HSL numbers, which is going to be to answer the following question. So here's motivating question number 1. Which is, can you compute the Frobenius closure? To compute the Frobenius closure amounts to finding where this stabilizes. So this amounts to finding eta. Yes. And once you know at which point this stabilizes, then you know how to compute this. Second question is there a eta that works for all I? And if this doesn't work, then is there an eta that works for all I in an interesting family? So I don't want to keep you in suspense, and I'm going to give you the answers to this. So the answer to the first question is sometimes. The answer to the second question is no. And there is a counterexample due to Holger Brenner. And the answer to the third question is yes, using HSL numbers. Okay? So it looks as if HSL numbers can do useful things, so I should tell you what these HSL numbers are. And here it comes. Frobenius maps and HSL numbers. So we're going to look at some R module. So let M be an R module. So we want to define a special kind of functions on this R module. So an additive function, which I'm going to call phi from M to M, is a Frobenius map. So this is going to be a generalization of this Frobenius map over here, only defined for modules. If phi of something in the ring times something in M is R to the P times phi of something in M. So it's not R linear, it's R to the P linear. If I have such a thing, where shall I write this? Such a Frobenius map phi is nilpotent. So that's what I'm defining here. If for all n in M, there is an E greater or equal to 0 such that phi to the E of M is equal to 0. Okay? So here's the central theorem that is going to underpin everything I'm going to do in this talk. So this was first proved by Hartshorne and Speiser. Hartshorne and Speiser in 1977. And later it was done in the general case by Lubeznik in 1997. And it says the following. If phi is nilpotent on an Artinian R module M, there exists a eta greater or equal to 0 such that phi to the eta of M is 0. So what's going on here? Every element has a power of phi that kills it. This is saying there's a power of phi that kills all the elements in this Artinian ring, this Artinian module. Okay, so this is trivial if M is finitely generated, but we are interested in big things, and which is going to be what I'm going to be doing next. Now, let me have a look at these numbers again. I want to define the HSL number, which is what is mentioned in the title of this talk. The smallest such eta is the HSL number. Now you know what it's called, why it's called an HSL number, Hartshorne-Speiser-Lubeznik, of phi on M. So let's see an example of that. And this is not just an example, it's going to be an ingredient of a proof. So this brings us to the next section. Actually, you remember the title, don't you? So that's the next section, and it's an example. And it's Frobenius maps on top local cohomology module. Cohomology modules. So now I want to look at a special kind of ring. So it's still characteristic P. I want it to be local. I want it to be Cohen-Macaulay. I'm going to pick a system of parameters X, which is X1 up to XD, a system of parameters, which is also a regular sequence since we're working in the Cohen-Macaulay ring. And I'm going to define the following object. So I'm going to call this object H. Let me make some room. Can you see here? Or okay. So H is going to be a direct limit of something. So the direct limit is going to be, first we're going to start with R modulo the ideal generated by the x's. And then I'm going to map into R modulo the ideal generated by the squares of the x's. And the map from here to here is going to be given by multiplication by pi. And pi is the product of the x's. And I can keep on going. And I can map in R modulo the ideal generated by the cubes of the x's and so on. This gives me a direct limit system, and I can take the direct limit of that. And this is my H. Now, many of you are recognizing what this is. This is the top local cohomology, the dth local cohomology. So buried in here is the notation that D is the dimension of the ring. So I'm looking at the dth local cohomology which supported the maximal ideal of the ring R. Okay. So what I want to do next is I want to define a Frobenius map on this non-finitely generated module. I'm going to note that this is an Artinian module. And then I'm going to use the HSL theorem. So let's define the Frobenius map. Phi from H to H. So what do I have to do to define this map? You give me an element in the direct limit, which is represented by some element in one of these quotients. So here's one of them. So it's the coset of A in the ideal generated by the ith powers of the x's. And I have to tell you what phi of this is. And it's going to be A to the P. The coset of A to the P in the ring modulo the I to the I times pth powers of the x's. And you can verify that this is indeed a Frobenius map. And if this is a Frobenius map, let's try to find a submodule of this. So I want to talk about the submodule of H, which is defined using phi. This is going to be the set of all the elements in H, such that this map phi iterated ith times kills it for some e greater or equal to 0. For some e greater or equal to 0. Now, let's have a look at this module of nilpotence, the submodule of nilpotence. How can I get phi killing things here? So first notice that all the maps here are injections because the X is from a regular sequence. And now let's see what gets killed by a power of phi coming from here. So when do I have a to the p to the e plus x to the I p to the e is 0? Well, this happens when a to the p to the e is in this ideal. Sorry, I don't need an I here, so I'm starting with something in here. So I is 1 here. So when do I get this vanishing for some value of e? This is the same thing as saying a to the p to the e is in x to the p to the e, which is another way of saying that a is in the Frobenius closure of I. And I can do the same calculation if I choose a representative coming from any one of these. So if I choose something in the ith piece here, I'm going to get this. And then this is going to tell me that, sorry, I didn't tell you what I is, so let me replace this with something that makes sense. So originally I wanted to say this is in the ideal generated by the X's Frobenius closure. And now if I start with something on the ith piece here, I'm going to get something in the Frobenius closure of the ideal generated by the ith powers of the X's. So if I write down, and notice that once to get an image which is 0, an image that Frobenius mapped that is 0, it's enough to be 0 here, because you don't need to go further along the direct limit system. All the maps are injective. So this is telling us that this submodule of nilpotence n is a direct limit of the Frobenius closure of the ideal generated by the X's, modulo the ideal generated by the X's, and this goes by multiplication by pi into the Frobenius closure of the ideal generated by the squares of the X's, modulo the ideal generated by the squares of the X's, and so on. Okay? Okay, so now we secretly know that this is a topological cohomology module with support at M. We know that this is Artinian. We know that we have a Frobenius map defined on H, which reduces to a Frobenius map defined on N. We know that N is defined precisely to contain the elements which are 0 under some power of phi. It's phi acts nilpotently on N. So now we're going to use the theorem, and it's going to tell us, so HSL says there exists an eta greater or equal to 0 such that phi to the eta restricted to N is 0. And what is this telling us? This is telling us if Frobenius takes something to 0 after E steps, it will take Frobenius, this Frobenius map is going to take it to 0 after eta steps. Which, if you write down carefully what this means, it's telling you that if you expand if you want to know what are the things that land in x to the I to the p to the e for large e's, which is what this is computing for you, it's enough to expand your ideal x to the I eta times using the eta's Frobenius map and then to contract back. And that's another way of saying for all i's, if you look at the Frobenius closure of the ideal generated by the ith powers of x, and then it is to the p to the eta power. That's the same thing as the ideal generated by the ith powers of the x's to the Frobenius p to the eta powers. So if you're trying to compute the Frobenius closures of ideals of the form x to the I, you know how to do that. Or at least you know that you can find an eta that works for all of them. Okay? So we can take this little example and we can change it a bit, and we can turn this into a proof of theorem, which is the following theorem. So I'm answering the third part of the motivating question. Is there an eta that works for a family of interesting ideals? So in this case, the family of interesting ideals is going to be all parameter ideals, all ideals generated by part of a system of parameters. So playing around with this example, we get the following theorem. So that's me and Rodney Sharp. And it says, so let eta be as in the example. Then for any system of parameters, any part of a system of parameters, we have the Frobenius closure. If you want to compute the Frobenius closure of the ideal generated by the system of parameters, it's enough to expand eta times and to contract. So I'm going to write this as the Frobenius closure of x to the p to the eta is the same thing as the Frobenius power of the ideal generated by x's. Okay? So we solve problem number 3 under the assumption that we're working in a local Cohen-Macaulay ring and our interesting ideals are ideals generated by parameters. You can do better than this, and this is really what I was striving to show you. So shortly after that, we improved this, but now it required quite an effort. So myself and Craig Huneke and Rodney Sharp and Yongwei Yao, and this was in 2006. And later, Kui, I'm not sure I'm pronouncing this name right. Does anyone know how to pronounce this name? Kui? Kui, okay. In 2019, very recent, you can show the following. There exists a eta greater or equal to 0 such that for all ideals I generated all ideals I want to expand the class of rings I'm working with, all ideals in a generalized Cohen-Macaulay ring generated by part of a system of parameters. All ideals I, we have, if you look at the Frobenius closure of this ideal, it's enough to compute it using these eta steps. So I'm going to write it as the Frobenius closure of f to the Frobenius p to the eta is the same thing as I to the Frobenius p to the eta. Now, I owe you some things here. I have to tell you what generalized Cohen-Macaulay rings. Now I'm going to owe you a bit more. I'm going to tell you something about this eta. This is what makes this theorem really interesting. So Cui gave a much simpler proof than our proof, and he gave a very explicit value for this eta, and he showed that eta can be written as, or can be chosen to be less or equal to the sum k goes from 0 to d, which is the dimension of our ring, d choose k, times something that I'm going to have to explain a bit later. I'm going to write HSL HKM, that's the kth local cohomology module with supported M of our ring R, our generalized Cohen-Macaulay ring R. So I have to tell you what I mean by generalized Cohen-Macaulay rings. I'm going to have to tell you what I mean by local cohomology modules, and I'm going to have to tell you what I mean by HSL numbers of local cohomology modules. Sorry? The HSL number. Okay, so let me try to explain what these different things mean, which brings us to the next section. There is a book, a very good book on local cohomology called 24 Hours of Local Cohomology, which is authored by some people in the audience. And I'm going to give you my version of this book, which is 3 minutes of local cohomology. Okay, so Frobenius and local cohomology. So here's what local cohomology is, formally, but if you haven't seen this before, this is going to make very little sense. So for an ideal I, we define a left exact functor, which I'm going to call gamma I, which is going to take R modules to R modules. And the way you define this is that if you apply this to a module M, then this is going to give you the submodule of this module M, which consists of elements with some property. And the property is that I to the k kills this M for some k. Okay, so you can apply this to modules, R modules, and you can apply this to maps between R modules. That gives you a functor which is left exact. And now we can take the right functor of the left exact functor gamma and define the ith local cohomology modules with supported I to be the right functor of gamma I. Now, this is not necessarily the best way to think about local cohomology. You can see this from the first example we had, in which I wrote down a direct limit that gives you local cohomology. So that's not the best way to do this, but that's the only way in which I can do this in 3 minutes. So here's local cohomology. So now, oh, sorry, I forgot to write equals 0. So this equals 0. Thank you. Okay. So why are we interested in this? Well, we saw why in the first example, but here are some interesting facts. So these FEs that go from R to R, these extend to Frobenius maps. These R to the P linear maps, to Frobenius maps on the local cohomology modules with supported I of the ring. The second interesting fact that we're going to use, so that's fact number A, here's fact number B. If you look at the local cohomology which supported the maximal ideal, oh dear, these are Artinian. And now let me tell you what the different components. Oh, I shouldn't. Okay. Okay, I want to keep the generalized Cohen-Macaulay ring. So what is that? I call R generalized Cohen-Macaulay if these local cohomology modules with supported the maximal ideal, they're all finally generated below the dimension of the ring. So that's what generalized Cohen-Macaulay means. Now, what are the other components I have to tell you about? So I told you what I pretended to tell you what the local cohomology modules written in this sum mean. But now I'm going to tell you what the HSL numbers are. So HSL of the ith local cohomology of R is the HSL number of submodule of nilpotence. This exists and is finite because of the fact that these local cohomology modules are Artinian and the HSL theorem. So this is well defined. And now I want to define also the HSL of R. And this is going to be the maximum of all the HSLs of I's, the HSL numbers of the ith local cohomology modules of R. And again, this is some finite number. Okay? And I'm going to call R F injective if all the Frobenius maps and all the local cohomology modules are injective, which is the same thing as saying that HSL of R is 0. Okay. Now, we've seen one application. I want to tell you about the second application of HSL numbers. And to do that, I have to teach you some more commutative algebra. So let me tell you in 3 minutes something else. Let's look at multiplicities, multiplicity and reductions. So again, we're going to restrict ourselves to local rings, and we're going to look at an ideal which is M primary. And we're going to look at the Hilbert-Samuel function of I. So that's a function that takes n to the length of R mod I to the I plus I to the power n plus 1. So that's the Hilbert-Samuel function. And now for large n's, so there exists a polynomial, which I'm going to write as pi of n, such that hi of n is pi of n for all large n's. And I can look at this polynomial and I can write down the various coefficients specifically, and I'm going to write it as EI R divided by d factorial, and again, d is the dimension of our ring R, times n to the d, plus I'm going to have lower terms. And if I look at this number here, EI of R, I'm going to call this the multiplicity of I. Okay. So what do I want to do next? I want to find a bound for multiplicities using HSL numbers. So how do I do that? let's see, I'm running out of time. Okay, let me tell you what the reduction is. A reduction of M is an ideal J that lives inside M with the property that M to the n plus 1 is J times M to the n for large n's. And if J is minimal with respect to inclusion, we call it a minimal reduction. So this is what I'm defining for you here. And these are going to be the ingredients that we need to bound multiplicities. So here are some facts. Fact number A is that minimal reductions exist if R contains an infinite field, which is a case we can always, in our case, we can always reduce to this, an infinite field. The second fact is that they're minimally generated by part of a minimal set of generators of M. And the third property we're going to use, which is the most relevant one, is that you can show that if you're trying to compute the multiplicity of the maximal ideal, then this is less or equal to the length of R modulo this minimal reduction. Okay. Okay, so what are we going to do with all this? I'm afraid I'm going to have to talk at least until 9:45, so please bear with me. So some time ago, so that's the new sections, which is bounds on E. So there's a theorem proved some time ago by Huneke and Watanabe. That says if the ring is nice, you can bound the multiplicity. So if R is F pure, then the multiplicity is less or equal to the dimension of the ring, choose V, where V is the embedding dimension. Okay. And here's an improvement to that. Yes. Oh, sorry. I'm sorry. It's the embedding dimension, choose D. Much better. Otherwise, otherwise we would be out of our jobs. Okay, so here's an improvement to this theorem, or well, a different case in which you can do this. So we don't know what F pure means, and I don't want to get into there, but here's another class of nice rings that you define by looking at Frobenius, which is if Rm is Cohen-Macaulay and F injective. Now we all know what F injective means. So all the Frobenius maps in local cohomology are injective. Then we have the same bound. We have the multiplicity of the ring is bounded by the embedding dimension, choose the dimension of the ring. Okay. Let me give you the best version of this, and let's see then how much time I have to prove any of that. And the theorem, which generalizes everything, is if R is Cohen-Macaulay on the punctured spectrum, so it has an isolated non-Cohen-Macaulay point, punctured spectrum, and if eta is the HSL number of R, actually HSL number of the topological cohomology module, so it's smaller, then the multiplicity of the ring is less or equal to P to the eta embedding dimension minus dimension times embedding dimension choose D. Okay, let me just, instead of giving you the proof, I don't want to steal too much time, so let me just give you the crucial ingredient in this proof. So what is it that makes everything work? So we start by choosing a minimal reduction J for our maximal ideal M, and we look at J to the D plus 1, and we look at the integral closure of that. And the crucial fact is that this lives inside the Frobenius closure of J. I told you that Frobenius closures are useful, so here's a use for them. Now, in our case, in the case of F-injective modules, how do we compute Frobenius closures? We have to expand by Frobenius eta steps, HSL number steps, and then contract back. In the F-injective case, the HSL number is 0. So we have to expand 0 steps and contract back. In other words, we're getting the same thing as J. And now you can do some calculations, and you can discover that M to the D plus 1 lives inside there. And we use the fact that we can bound the multiplicity by the length of R mod J. When you think about what is the dimension of this is a K-vector space, so you're going to get something spanned by monomials in the generators, the minimal generators of the maximal ideal, and you do the calculation of which monomials survive when you kill J, and then you're going to get precisely embedding dimension, choose dimension. Okay, it's a beautiful proof. If you want to see it, come to me after this talk and I'll show it to you. Okay, thank you very much.
Questions, comments, Fabian?
You started off with a Frobenius map, R goes to R to the P to the E having nothing to do with this E. But it just seems for a Frobenius map on a module, shouldn't it be P to the E linear rather than P linear?
Right, so okay, so what the definition I gave is a P to the 1 linear.
Yeah.
You can have P to the 2 linear and so on.
Yeah, so if you want this induced map on local cohomology, it ought to be P to the E.
Well, you start with a P to the 1, and then iterations of that give you P to the 2.
Yeah. Okay.
It's the same thing as the map, the Frobenius map on the ring. You start with taking.
Yeah, sure.
When these equalities to equalities.
That's a great question. So this bound is sharp. This bound is sharp, or asymptotically sharp, I should say, but let's not get there. So I can construct families of examples in which the multiplicity is this.
Any other question? I have just a question. You said that there is this counterexample by Brenner.
Yes.
And so it's out the situation situation where you have system parameters.
Yes, that's right.
Is it too complicated?
I suspect it's not too complicated, but I can't remember it. But I can give you a reference to it.
I have a question. The family form for, to illustrate this asymptotic sharpness is over hypersafe rings, if I remember.
Yes.
Hypersafe. Do you have any clue about extending this family for complete intersections of higher dimension? Or examples verified?
Okay, so what are the hypotheses here? I need Cohen-Macaulay in the puncture spectrum. So as long as you give me one of these, which would include all the hypersurfaces and all the complete intersections, then you get this bound. Oh, so you want examples in more complicated cases? Yes, I guess I could try and find more exotic examples, but if I have a simple example, I'm happy with that. Yes?
What is the bound for characteristic 0 in this theorem of
Gosh, you asked really good questions.
less than equal to
Okay, so in characteristic 0, none of this seems to be making any sense. But okay, if you take an homogeneous hypersurface and you compute the multiplicity is the degree of the hypersurface. So you're not going to get any bounds in general in terms of dimension and embedding dimension. So if you're going to get such bounds, they have to come from especially nice rings.
we have rings of minimal multiplicity where multiplicity is bounded below by v minus d plus 1. But this is an upper bound.
Yes. Right. So the fact that this is an upper bound and it's very easy to construct very large multiplicities tells you that you have to be very, very choosy with your rings. But you said something about characteristics here. So you can take this and you can say, let's work in characteristics here. Instead of looking at F-injective rings, let's look at rings of F-injective type, which means that when you reduce modulo a prime, you get something which is F-injective for almost all primes. And then if for almost all primes you get something F-injective, you get the same bounded multiplicity.